Cool. So today, the objective is to understand mathematical logic, and this is the fourth lesson of our introduction to computing mathematics. So mathematical logic is the study of reasoning using formal methods and symbols. In computing, it plays a fundamental role in developing algorithms, writing conditional statements, constructing control structures, and designing hardware logic circuits. It allows for decision making within programs and is essential for ensuring correctness, consistency, and reliability in both software and hardware systems. Mathematical logic forms the basis of many areas of computing, including programming, data validation, software testing, artificial intelligence, and digital electronics. It allows for computing professionals to express rules, solve problems, and control systems using well-defined logical relationships. So what is mathematical logic? Mathematical logic is a subfield of mathematics that deals with statements, also known as propositions, that are either true or false, logical operators such as and, or, and not, implication and equivalence, truth tables and represent logic outcomes, rules of inference and proof systems. It provides the framework to formulate logical expressions and deduce conclusions from known information, core to computation. Proposition. A proposition is a statement that is either true or false, but not both. For example, the user is logged in or the file is corrupted. Logical operators, as you can see below in the table, they're and, or, not, implication, and biconditional. And the symbol is shown above here in the table. Here's the meaning. So and means if both are true, true if both are true, or is at least one needs to be true, not inverts the truth value. Implication, if A is true, then B is true. And biconditional, A and B are both true or false. And this is how you notate them, as shown in the example. An example in programming is shown below. So if is logged in and has permission, access granted equals true. So this is an and operator being used because it checks if both statements are true. And if they are true, then the following logic will be executed. Truth tables are used to show all possible truth values, of logical expression. As you can see in the table below, these help in evaluating expressions and designing logical systems such as login validation. So as you can see, it says A is true, B is true. So A and B will be also true because both are true. A or B will be true because one of them is true, and not A would be false as A is true. Similarly here, we'll do the second one as well. A and B will be false because both are not true. A or B will be true as one of them is true, and not A will be false again as A was true, and so on. Logic gates implement logical functions in hardware. AND gate, only output is high only if all inputs are high. OR gate, output is high if any input is high. NOT gate inverts the input. These are used in processors, memory circuits, and embedded systems. So programming. Logical conditions determine program flow using if, while, and for structures. An example is shown in the code where it uses a conditional if statement to check if the age is greater than 18 and if the variable is registered is also true. If both are true, using the AND operator, then it will execute the allow access function. Database queries. So SQL uses logic in where clauses to filter results. For example, select everything from users where age is greater than 18 and country equals UK. So this will check where the age is greater than 18 and also where the country equals to UK. So both of these have to be true for that to be executed. Software testing. Logic is used in test cases to ensure all conditions and branches are covered. For example, decision tables, boundary testing. Artificial intelligence, mathematical logic is used in rule-based systems and decision-making algorithms in AI. For example, a rule in a chatbot. If a user says hello and it's morning, then respond good morning. Cryptography. Logical operations are used in binary and bitwise computations to encrypt and decrypt data securely. Here's the summary table of mathematical logic within computing. I'll give you a minute or so to look at this and then we can move on. Cool, let's move on. If that's okay.
Yes, Mr. Hamza, we're done.
So the conclusion is that mathematical logic is a core concept in computing that supports reasoning, decision making, and control flow in both software and hardware systems. Through propositions, operators, truth tables, and logic gates, programmers and engineers can model problems and design solutions that are robust and logical. Its applications span across programming, AI, security, and data management, making it a vital area of knowledge for computing professionals. Mathematical logic provides a formal framework for reasoning, decision-making, and control flow in computing systems. It enables computers to make logical decisions, evaluate expressions, process inputs, and execute code based on defined rules. From simple conditional statements in programming to complex decision-making in artificial intelligence and hardware design, mathematical logic underpins nearly every computational process. Mathematical logic uses well-defined rules as logical operators such as and, or, not, to create expressions that return either true or false. These expressions control what the computer does at each step, making logic essential for tasks such as validating user input, controlling program execution, filtering data in databases, automating decisions in AI, simulating real-world scenarios. Without logic, computing systems would lack the ability to make decisions or respond to changing inputs, so significantly limiting their usefulness. Programming and control flow. Mathematical logic is embedded in programming languages through conditional statements, loops, and logical expressions. An example is in Python, where if the user is logged in and user has access, then if both of these are true, the program would print out access granted. And is a logical operator. The system checks if both conditions are true before granting access. This use of logic allows software to respond dynamically to different conditions, improving efficiency and user experience. Digital circuit design. In hardware systems, logic gates such as AND, OR, NOT, and XOR, sorry, are physical implementations of mathematical logic used to build microprocessors and memory systems. For example, an AND gate only outputs one only when both inputs are one. Logic circuits combine gates to perform binary calculation or store data. Mathematical logic enables digital devices to perform arithmetic, store instructions, and manage memory at the hardware level. Artificial intelligence and decision making, AI systems, and rule based engines use propositional and predicate logic to make intelligent decisions based on given rules. For example, chatbot uses logic to decide how to respond, i.e., if user says hello and time is morning, respond good morning. Logic allows AI systems to process knowledge, evaluate rules, and act autonomously. Digital queries and filtering. SQL uses logic in where clauses to retrieve specific data based on conditions. For example, shown here, select everything from employee where age is greater than 30 and key is and department equals sales. The query returns only records that meet both conditions, logic and is applied. Logical and is applied. Software testing and validation. Logic is used to design test cases, model decision paths, and identify faults. Logical expressions ensure that all possible conditions, true/false combinations, are tested to prevent bugs. For example, a test might check if input is valid and user is active, allow transaction. Logical expressions from the basis for decision tables and truth tables used in software quality assurance form the basis. Encryption and security. Cryptographic algorithms rely on bitwise logical operations to encode and decode data securely. For example, XOR encryption uses logic to scramble data in ways that can only be reversed with the correct key. Mathematical logic ensures that data integrity and confidentiality of data is in digital communication. Here's a table of what was a summary of the use of mathematical logic on computing. Give you a minute or so to look at it, and then we can move on. Cool. We'll
Yes,
move.
we're done.
Yeah, cool. We'll move on from here. Conclusion here is that mathematical logic is an essential component of computing, enabling systems to process instructions, make decisions, and perform actions based on rules and data conditions. Its application ranges from software development and AI to databases and cybersecurity. Whether through logic gates in hardware or conditional statements in software, mathematical logic gives computing systems the ability to act intelligently, reliably, and efficiently. So, explain how Boolean logic is used. Boolean logic, also known as Boolean algebra, is a fundamental branch of mathematical logic that deals with binary values, true and false, or one and zero. In computing, Boolean logic is used to control decision making, define conditions, and process data efficiently in both software and hardware systems. Developed by George Boole in the 19th century, Boolean logic uses logical operators such as and, or, and not to combine or manipulate true-false values. These logical expressions form the basis of programming control such as search filters, conditional statements, digital circuits, and more. So Boolean logic involves operations on variables that can only have two values, true, which is one, and false, which is the binary zero. These are manipulated using Boolean operators, including and, or, and not, which we have discussed previously. Additional operators often used in computing include XOR, which is an exclusive OR, and this is true if only one input is true. NAND is the inverse of and NOR is the inverse of OR. Programming and control structures. Boolean logic is embedded in conditional statements if, else, while, and for to determine which actions a program should take. For example, the code below, as we discussed before, if is logged in and has permission, then it would print out the following message onto the console. Is logged in and has permission of Boolean variables. If both are true, access is then granted. Search engines, databases, and e-commerce platforms use Boolean logic to refine and combine search results. For example, searching for a laptop and SSD and not used returns only new laptops with SSDs. For example, select everything from product where laptop and stock is greater than zero and not refurbished. The hardware, digital electronics, and logic gates. At the hardware level, computers operate using logic gates that physically implement Boolean operations. These gates process binary signals, ones and zeros, to perform calculations and control data flow. AND gate outputs one only if both inputs are one. OR gate outputs one if at least one input is one. Not gate outputs the opposite of the input. These are used in microprocessors, memory units, and digital controllers, artificial intelligence and rule-based systems, AI systems, and expert systems apply Boolean logic to make decisions based on conditions. For example, a smart home assistant may respond if motion detected and time is night, turn on the lights. Software testing and validation. Boolean expressions are used to test combinations of inputs and ensure all logical branches of a program work correctly. For example, if condition A or condition B is true, the system should perform condition X. Truth tables are used to illustrate how Boolean expressions behave under all possible input combinations. For example, A and B. If A is 0 and B is 0, A and B would be 0. If A is 0 and B is 1, A and B would be 0. If A is 1 and B is 0, A and B would be 0. However, if A is 1 and B is 1, A and B would be 1. Truth tables are both vital in software logic and digital circuit design for verifying input. Real world example, so a login authentication system, the code is shown below. If user name is correct and the password is also correct, so if both of these conditions are true, then the access is granted. Otherwise, access is not granted. This uses AND logic to ensure both conditions are true before allowing access, and it improves system security by validating multiple criteria. Here's a table of summary for how Boolean logic is used in computing. I'll give you a minute or so to look at this and then we'll move on. Cool. Let's move on.
Yes, we're done, Mr. Hamza.
So the conclusion is that Boolean logic is at the core of computing. It allows systems to make decisions, evaluate conditions, and process binary data, whether embedded in software programs, database queries, AI systems, or hardware logic gates. Boolean operations help computers function reliably and efficiently. Mastering Boolean logic is a foundational skill for all computing professionals and essential for designing intelligent, secure, and responsive systems. Explain the logic gates used in calculation. Logic gates are the basic building blocks of digital electronics. They are electronic circuits that execute Boolean operations such as AND, NOR, OR, and NOT, and their combinations to process binary data. Logic gates perform fundamental calculations at the hardware level and are essential in construction processors, memory systems, control circuits, and other digital devices. Each gate processes input signals and produces an output based on defined Boolean logic rules. These gates are used in arithmetic logic units, ALUs, calculators, and embedded systems to perform decision making and calculations in digital formats. At the AND gate, so A and B, like we've seen before, the truth table, and these are used in calculations. AND gates are used in systems that require multiple conditions to be true, such as enabling a security system only if two switches are activated. Here's the OR gate. Output is true if at least one input is true. The truth table here is that 0 is A and B is 0, then A or B is 0. If A is 0 and B is 1, then A or B is 1. If A is 1 and B is 0, A or B is 1. And if A is 1 and B is 1, A or B is 1. These are used when any condition can activate an output, for example, starting a machine if either one of the two safety switches is pressed. NOT gate, the symbol is shown there. Operations inverts the input. If the input is 1, output is 0, and vice versa. The truth table is shown below and used in control logic, for example, denying access when a condition is not met. NAND gate operation is to inverse of the AND gate. returns false only when both inputs are true. So the truth table for this is shown there. And this is used in memory circuits and processor instruction logic due to their simplicity and reliability. The NOR gate is the inverse of the OR gate and returns true only when all inputs are false. So this is used in reset circuits and state machines. The XOR gate, the output is true when only one of the inputs is true, but not both. This is used in arithmetic operations such as binary addition, parity checks, and cryptography. As you can see, when both statements in the truth table are the same, for example, if both are false, A and B are false, then A XOR B will be 0. And if A and B are true, so 1, then A XOR B will be 0. However, if A and B differ, then A XOR B will be 1. The XNOR gate, the exclusive NOR gate, is true when both inputs are equal. This is the inverse of XOR, used in comparator circuits to check equality between binary values. Here's real world use of logic gates in computing calculations. So binary adders, XOR gates for sum, and AND gates for carry bits. Microprocessors, the logic gate uses combined AND or not NAND gates to perform arithmetic and logical operations. Memory storage, NAND and NOR gates store bits in flip-flop circuits. Digital clocks and counters, logic gates manage timekeeping and state transitions. Authentication systems use AND gates to verify multiple conditions before granting access. ALUs use a combination of logic gates to execute mathematical operations. Here's a summary table of logic gates and their role in calculations. And I'll give you again a minute to have a look at this. Just note the symbols for notation, especially with the XOR and XNOR, and also NAND and NOR for the future. Cool. Let's move on then, guys.
Yes, we're done.
Logic gates are fundamental to performing calculations in digital systems. They implement Boolean logic operations in hardware and software to process binary data, make decisions, and control electronic systems, whether in microprocessors, memory modules, or software-based simulations. Understanding how logic gates function and interact is essential for anyone working in computing, electronic, or embedded systems. In compute, describe arithmetic and relational operators. In computing, operators are symbols or keywords used in used to perform operations on data. Two of the most commonly used categories are arithmetic operators and relational operators. These operators form the foundation of programming and computational logic. They enable mathematical calculations, comparisons, and decision-making in software algorithms and data analysis. Understanding how these operators work is essential for creating functional programs, validating data, and controlling the flow of execution based on mathematical or logical conditions. Arithmetic operators are used to perform mathematical operations such as addition, subtraction, multiplication, and division. They are essential in calculations related to finance, science, engineering, gaming, and general data manipulation. Common arithmetic operators are shown in the table below: addition, subtraction, multiplication, division, modulus, exponentiation, and floor division. Addition, subtraction, multiplication, and division are self-explanatory. Modulus returns the remainder of the division. For example, 10 modulus 3 would return 1 because 10 divided by 3 is 9 and there's 1 remainder. Exponentiation raises left to the power of the right. So 2 to the power of 3 equals 8, 2 cubed. Floor division returns the integer part of the division. For example, 12 divided by 5 is 2, remainder 2, but it returns 2 as that is the integer part of the division. This is the use in computing is calculating totals and averages, financial computations such as interest and tax, game scoring systems, graphics and motion calculations, and statistical functions. Relational operators, also known as comparison operators, are used to compare two values in expression. The result of a relation operation. Relational operation is always a Boolean value, true or false. These operators are widely used in control structures, filtering data, and validating user input. An example is shown in the tables: equal to, not equal to, greater than, less than, greater than and or equal to, and less than or equal to. The use of this is that for making decisions using if statements, loop control conditions such as while and for, data validation such as password length check, search and sort algorithms, conditional access control, for example, age is greater than 18. Real world example in program. So a user age is 20, ticket price is 10.0. If user age is greater than 18, adult ticket with the ticket price else, print child ticket with the ticket price multiplied by 0.5, which gives a 50% discount. The arithmetic operator is multiplication used to calculate the 50% discount. Relational operator is the greater than and or equal to used to check if a user is an adult. Summary table for arithmetic operators and relational operators are shown above. The conclusion is that both arithmetic and relational operators are fundamental tools in computing that allow programs to calculate, compare, and make decisions based on input and conditions. Arithmetic operators are used for numerical processing, while relational operators enable comparison and logical control flow. Together, they form the basis of computational logic used in programming, data analysis, AI, software testing, and much more. Describe the use of truth tables. Truth table is a mathematical table used in logic, particularly in Boolean algebra and digital electronics, to determine the truth value of a logical expression or compound statement based on all possible input combinations. In computing, truth tables are used to verify logical expressions, validate program logic, and design digital circuits. Truth tables provide a systematic way of displaying the output of logical operations, making them a vital tool in programming, software testing, computer hardware design, and artificial intelligence. The purpose of a truth table in computing. Truth tables serve multiple purposes in computing, for example, evaluating logical expressions, designing and testing digital circuits, verifying the correctness of conditional statements, visualizing and simplifying Boolean expressions, and to assist in software testing by analyzing logical conditions, by listing all possible combinations of inputs and showing the corresponding outputs. Truth tables help ensure that all logical paths have been considered, particularly useful in debugging, logical validation, and circuit simulation. The structure of a truth table is that a truth table typically contains columns for each input variable, a column for each intermediate expression, and the final column for the output of the full logical expression. And we've seen these before, the truth tables for and or. And an explanation could be that for and, the output is 1 when only both outputs A and B are also 1. And the output is 1 if at least one of the outputs is 1 in an OR operator. Not operator just does the opposite of the input. Truth tables are essential in designing digital circuits and microprocessors. Engineers use truth tables to determine how logic gates will respond to different input combinations. This helps them ensure circuits behave as intended and that all input possibilities are covered. For example, designing a circuit to control whether a light turns on based on 2 switches. Light turns on if either switch is on. Use an OR gate for this, and truth table confirms the logic. Use in software development. Truth tables are used by software developers to model and test conditional logic, ensuring that every branch of logic in an if-else statement functions correctly. For example, if user is admin and user has token, access is granted. A truth table can be constructed to test every possible combination of the conditions. Used in Boolean expression simplification. Truth tables also help simplify complex Boolean expressions using techniques such as Karnaugh maps. This is useful in improving the efficiency of digital logic circuits and reducing the complexity of conditional call. Sorry. Here's a summary of uses of truth tables in computing. Have a little look at that and then we'll move on.
Yes, we're done.
Cool. We can conclude here that truth tables are essential tools in computing for analyzing, designing, and verifying logical systems. By showing how inputs affect outputs, they enable developers and engineers to model accurate logical behavior in software and hardware. Truth tables are not only crucial for designing digital circuits and writing robust code, but also for testing systems. validating the conditions, and optimizing performance through simplified Boolean logic. Perform simple calculations and apply logical expressions. In computing, the ability to perform simple arithmetic calculations and apply logical expressions is essential for building functional software, validating input, handling data, and managing control flow. These two elements, calculation and logical expressions, often work together in programs, supporting everything from basic math operations to complex decision-making algorithms. Simple arithmetic operations include addition, subtraction, multiplication, division, modulus, exponentiation, and floor divisions, like we have discussed before. An example is the code shown on the right, where the item price is 15, the quantity is 3. The total cost is the item price multiplied by the quantity. So, and this would print out total equals the total cost, which is 15 times 3, which is £45. This example uses multiplication to calculate the cost of multiple items. Logical expressions are used to evaluate conditions. These are made using relational operators such as greater than, less than, equals to, not equals to, greater than or equal to, less than or equal to, and Boolean operators such as and, or, and not. Logical expression in Python is shown below. Age is 20, has ticket is true. If age is greater than 18 and has ticket is true, print that access is granted, otherwise say that access is denied. And the output here would be that access is granted as the age is greater than or equal to 18, and also the has ticket variable is true. And here it is common to combine arithmetic operations with logical conditions. For example, discount application is shown. So the cart total is 120. If cart total is greater than 100, discount is cart total times 0.1, which gives a 10% discount. The final price is cart total takeaway discount. And here it would print out the final price and what is and the variable final price. If we check this, we do 100 times 0.1. Sorry, 120 times 0.1, which is 12. Then we take away 120, take away 12, which is £108. The example uses arithmetic to compute the discount, logical expression to check if a discount should be applied. Let's consider a condition if age is greater than 18 and is a member. Using our truth tables for and here, if both are false, we will return false. If one is false, we would return false. However, if both are true, we would return to true. We also have scenarios. So e-commerce checkout calculation is total price multiplied by quantity. And if the total is greater than 100, apply the discount. Age-based access control. Age equals current year minus birth year. And the logical expression could be if age is greater than or equal to 18. Password validation. Count length of the string. If length is greater than or equals to 8 and contains special character. Test grading. Average equals the score 1 plus score 2 divided by 2. If average is greater than 50, and then do a condition for passing or failing. Game scoring. Score equals hits times 10 plus bonus. If lives is greater than 0 and score is greater than or equal to 100, advance to the next level. Here's a summary table of calculations and logic in practice. The conclusion here is that performing simple calculations and applying logical expressions are foundational skills in computing. They enable software to interact with users, process data accurately, and respond to real-world conditions through rules and decisions. Whether checking a user's age, calculating order totals, or validating inputs, these functions form the basis of most software applications. Use mathematical logic techniques to make informed decisions based on data analysis. Mathematical logic techniques are widely used in computing to evaluate data, draw conclusions, and support decision making. These techniques include Boolean algebra, logical operators, truth tables, and conditional expressions, which allow systems to develop and developers to process structured information and generate reliable outcomes. In the context of data analysis, logical techniques help filter data, identify patterns, and automate responses. Sorry. By applying logic, decisions become systematic, consistent, and data driven, which is especially important in domains like business intelligence, cybersecurity, artificial intelligence, and system control. Boolean logic evaluates expressions as true or false, uses logical operators and or not and XOR, helps define conditions for action. Truth tables used to represent, evaluate all possible outcomes of a logical expression. This ensures all conditions have been considered and tested. Conditional logic, if statements implemented in code to make automated decision based on evaluated conditions, allows branching logic depending on data values. Logical filtering, applied in databases, spreadsheets, and scripts to isolate specific records or trends. The scenario is shown below, where an e-commerce company wants to segment customers for a marketing campaign using the following criteria: customers who spent over 200 in the last month and made at least 2 purchases and are subscribed to the newsletter. The sample data is shown below, where Alice has spent more than 200 and has made more than 2 purchases, therefore she has subscribed, so she fits the criteria. Bob has spent less than 200, so he does not fit the criteria. Claire has spent more than 300 and made more than 2 purchases. However, she has not subscribed, so she does not meet the criteria. David has spent less than 200, so he does not meet the criteria. And Eve has made at least 2 purchases, has spent more than 220, and is subscribed. Spent more than 200, sorry, and is subscribed. Therefore, she meets the criteria. Below is just the code you would write for this in Python. The truth table discusses exactly what I discussed before, showing that Alice and Eve are the only 2 that fit the criteria, and they are selected for the campaign. Benefits of using logic in data analysis: consistency. So decisions are based on defined logical rules rather than subjective judgment. Efficiency. Conditions can be applied to large data sets using scripts or queries. Scalability. Logic-based conditions can be reused or scaled for automated systems. Error reduction. Structured rules help avoid human errors in manual filtering, and insight generation allows identification of patterns and anomalies through logic-based filters. Other use cases are mathematical logic for decision making, spam email detection. The logic applied is if free in subject and sender not in contact mark as spam. Access controls and systems, if role equals to admin or user has token, then grant access. Student grading systems, if average score is greater than or 50, then pass. Smart home devices, if motion detected and time is greater than 10 p.m., turn on lights. Financial fraud detection, if transaction is greater than threshold and location is not usual, then flag the transaction. These examples show how mathematical logic helps automate and enhance decision-making across diverse applications. An example is shown in the code below for the sample of eligible for free shipping. Spend is 150, the country is UK, and the condition is if someone has spent at least 100 and is in the UK, they are eligible for free shipping, else they are not eligible for this. Mathematical logic techniques provide a powerful foundation for making informed decisions based on data. By applying Boolean logic, conditional expressions, and truth tables, computing systems can process large volumes of data efficiently and consistently. This leads to accurate outcomes, improved automation, and smarter business or technical decisions. Mastering these techniques is essential for roles in data analysis, software engineering, and digital systems development. Use truth tables to solve Boolean statements. Truth tables are essential tools used to evaluate Boolean expressions systematically. They list all possible combinations of input values and show the corresponding output of a Boolean statement. In computing, truth tables are used to verify the logic of expressions, design digital circuits, test algorithms, and ensure all possible conditions in a program have been considered. Purpose of solving Boolean statements with truth tables. Using truth tables allows us to analyze logical expressions, identify equivalencies and contradictions, test and verify logic gate combinations, simplify Boolean expressions, support decision-making in programming and system design. The first example shows solving a simple Boolean statement. The statement is A and B. This is an operation, and the truth table is shown below. The result is 1 only when both A and B are 1. Solving a compound Boolean expression. Statement is A or B and not C. This combines or and not. The truth table is slightly more complex as it has 3 values. And we can combine them together. So A and B, if all are 0, A and B is 0, not C is 1, and 0 and 1 is 0. For the second one, if C is 1 and the rest are 0, A and B, A or B will be 0, sorry. C will be 0, not C will be 0, and the result of that will be 0. If B is 1, then A or B will be 1, not C will be 1, and the result of that will be 1. If B and C are 1, A or B will be 1, not C will be 0, and the result of that will be 0. If A is 1, then A or B will be 1, not C will be 1. So 1 and 1 is 1. If A is 1 and C is 1, A or B will be 1, not C will be 0, and 1 and 0 is 0. If A and B are 1, A or B will be 1, not C will be 1, 1 and 1 is 1. And if all of them are 1s, A or B will be 1, however, not C will be 0, so A 1 or 1 and 0 is 0. The interpretation here is that the output is true only when A or B is true and C is false. Checking logical equivalence. Check if the following two expressions are equivalent. That was, sorry, let me just remember, that was A, not A, or B. So the truth table is shown below to check their equivalence, and the interpretation here is that the output columns for A to B and not A or B are identical, so the expressions are logically equivalent. As we can see in the truth table. Applying truth tables to a real-world decision scenario, a system should allow access if a user is an admin or the user is verified and the access code is valid. The Boolean statement is shown there, where A is admin, V is verified, C has a valid code. The interpretation here is that access is granted when the user is an admin or both verification and valid code are true. True meaning that the result of them both are 1. Benefits of using truth tables in computing: clarity and precision, provides a clear visual of how inputs affect outputs. Error detection helps identify faulty logic in programming or circuit design. Logic simplification, used to simplify complex Boolean expressions. Decision support ensures all logical conditions are evaluated before action. Foundational for the circuit design, essential in building logic gates for processors and hardware. Truth tables are powerful tools used to solve and analyze Boolean statements. By listing all possible input combinations and their corresponding outputs, truth tables help verify logic, detect errors, and simplify conditions. They are essential in programming, digital electronics, AI rule systems, and system design, making, making them a core component of mathematical logic in computing. The references for today are shown below with the reading and the sources that the information has came from. Again, like I say every time, further reading is important here. Any questions, feel free to ask me now, feel free to ask me in the group chat or email the following address. And the submission of the assignment is also emailed to the following address. And the assignment is submitted after 2 weeks of the completion of the units and its delivery. Thanks for your time, guys, this weekend. I hope it's been informative. I hope it's been helpful. If you've got any questions, ask me about now or even later about today's session or yesterday's or any session. But otherwise, you guys are free to go and have a nice rest of your weekend and week.
Thank you, Mr. Hamza.
No worries. Thanks a lot, guys.
Thank you.